Now, what really interests me is, and what I find totally amazing, is, why did I write this stupid convolution integral? I just gave it the rule and it works, but where did it come from? The intuition that Andrew so sorely lacks will now be supplied. And this comes from this fearful power of symmetry. This is a very literate reference to William Blake and Tiger, Tiger, Burning Bright. Everything we are doing is a consequence of translational symmetry. Only reason why we're doing this Fourier transfer complex, etc., is saying that we live in a world that, to good approximation, there is no center. Every origin is as good as any other origin. So I have translation. And we believe that in a fair and just world, the rules don't change from minute to minute. There is a immutable document which we originalists believe should never change, called either Bible or Constitution or Newton laws. And we know that while the first two are very immutable, Newton laws are given, or general relativity are given to measurements, and on a time scale that we are aware of and able to probe, they are immutable. So that's why we become physicists and not lawyers. How does this power of symmetry impose its thing? It actually tells us what laws are allowed. Assumptions of symmetry is the first thing we always do when we start writing our laws. So, for example, when we went to complex plane, we imposed, an off-the-wall law which said, look, in 2 dimensions we should have directional derivatives. So, how we take a derivative of a point, function at a point, has to depend on whether I'm going from northeast or I'm approaching it from the west. But Gauss and then Cauchy, Riemann said bravely, well, what if I assume there is a symmetry and it doesn't matter from which direction I approach it? What would be the consequences of that? Consequences are amazing, because assuming that it doesn't matter where you go, that's called conformal symmetry, gives us Cauchy-Riemann on differential version. But then in its integral version, the anti-differentiation gives us this amazing theory of complex analysis, which, we'll never stop loving because it's beautiful, it's amazing. Now, we have done the amazing thing now, but, we just didn't value it. So here we have decided that in Euclidean space, translation is sacred. But now I'll show you that translation, being sacred, gives amazingly strict condition of what all operations are, of which Toeplitz is just a simple case. So as long as operators can be written as matrices, they will all become some word that maybe you haven't seen. It's called Toeplitz. There's some random German engineer mathematician. So it's a very powerful constraint. And this convolution is a very powerful thing. So what's a symmetry? Symmetry says that if we have a matrix, any matrix. Now, in quantum mechanics, matrix is called an operator, and it's a rule which, if you express it in terms of some basis, it's a very large or infinite matrix full of elements saying that if you're in this state, this happens. If you're in this state, this happens, because Schrödinger said so, or Heisenberg. Symmetry means that this matrix must commute with the general of translations, meaning that it doesn't matter whether I first translate and then I apply my law, or I apply my law and then translate, results should be the same. Now I can multiply both sides from the right by inverse matrix. So another very common statement of symmetry says that object on the right, which you can understand, this translation operator is a permutation operation. So what it does is it changes coordinates. So if I change coordinates by inverse sigma, I do my MMMMM thing, and then I go back to original coordinates by sigma. So I went from here, I did this, and I come back. It shouldn't matter. I can do my experiment in Kyoto or in Atlanta. I should always get the same set of observables. So if this is a matrix, what does it do? The problem with lots of stuff that we teach is that there are too many things. So matrix is an array of numbers. I won't write them with indices or anything. It says at every slot here there is a number. So for example, there is a number here. Now, what does shift operation do? This is a column vector acted on the left by the shift. It says I end up here. So that's what shift operation does. It moves all the matrix elements one step up vertically. And, I'm just looking at one of them. It's this guy. Now, what is the inverse operation applied from the left-hand side? Now, this guy is acting on the row. So it's a matrix multiplied by vector from the left. So these are the rows of this thing. And this one says that if I had something here, then this will, put me here. So it's lowering, where am I in a row? So what's this operation? I look at the matrix element. And now, this operation puts it up, this guy puts it to the left, and I find out that this operation moves the matrix element to on diagonal. So here is a diagonal. And, it reappears over there, whatever it is. There is a diagonal. And this shift just moves the matrix element, but the law of nature, law of symmetry, says that it should have the same value. That means that everybody on diagonal is equal. So the translational symmetry is a very powerful requirement. It says that in order to be translationally invariant, the law of nature should be a circulant matrix. which means that all the entries on the diagonal are the same on every diagonal. So because of that symmetry, even though the matrix is nominally L cross L or N cross L, N, it actually has only N distinct elements. So this symmetry has reduced the dimensionality of your problem from being N squared just being N. Simple consequence of symmetry. Where did the convolution theorem come from? Why is it symmetries? All matrices used to be N cross N. So 7-dimensional was 49 elements. But now only N distinct ones. And that's what symmetries always do. They reduce the number of your options because symmetry is very constraining. You're not allowed to do anything to violate symmetry. So now the matrix looks like, something here. I'll indicate it in green. Something here.
Professor, we don't see the...
I was trying to keep it hidden from you because this is now secret knowledge for the Illuminati only. But it has a formula, so those morons would not be able to understand.
I must be telepathic.
I assume that you know what I'm doing without me showing you the vulgar paper. And so on, the numbers sit in diagonals. But we have a basis for that. We can write it as sum of j equals 0 n minus 1. Our shift matrix looks exactly like that guy, and to power j, it looks like a further j diagonal. And what it means is that when we go to our magical basis, which are the orthogonal vectors of the sigma matrix, we're supposed to replace every one of these guys by a number. Matrix gets replaced by a number in a good basis, right? Which is e to the 2 pi over n to the power j.
Wait, how many diagonals are there? It's n diagonals?
N, yeah. It's n by n matrix. So top row are n distinct numbers. Every row below is just cycled by one notch, cyclically permuted. It's only cyclically symmetric.
Okay.
It's only that,
I'm just think about I see the upper half triangle, right? It will have n different diagonals because you can have n different elements. The diagonal starts in the first row, right? And there's n elements in that row.
Yeah, so every color is a different number.
So then you also have n.
The next one cycles back, that's identity. So that's not a separate basis element.
Got it.
The independent matrices are sigma to the j smaller than n. So that's complete basis for this matrix. So it says any law of nature that I write, if I have translation invariance, is expressible in terms of the shift matrix, the one that I've been torturing with all the time. Or maybe in a more familiar way for you, it says that if I have any matrix element, I can always write it as in the top row, I minus j, 0. Anything that I can say, postulate, only depends on the relative distance. Only cares about the separations of the 2 points on my interval. Nothing can be expressed in terms of absolute position, which is what's expressed on the left-hand side, because that would violate translational invariance. And that's why they always keep telling you, you're looking at something, a Green's function, you started a y and it to x, but it's really function of x minus y. That's the thing that showed up in the convolution. if I take a Fourier transform of this matrix, I know that Fourier transform is there because it diagonalizes it. So Fourier transform has zeros every place except on the diagonal where it has eigenvalues. Now, these eigenvalues, we have them here. That's what this sum is. It's the value of lambda I. So now what's a convolution? What's your Andrew's intuition about convolution? Convolution is two things. One, because we have translational invariance, any operator is a Toeplitz matrix, meaning that it's a bunch of diagonals. It doesn't have n square elements. It has only n elements, cyclically arranged row by row. Number one. Number two, Fourier transform is a good transformation in that case because this is based on shift, so it commutes with the operator, which is operator of translation. So I'm allowed to use the eigenvalues of the translation operator to compute this matrix. That's why I'm allowed to write this diagonal form, which is non-trivial. I showed you one that was called propagator. It had 3 terms, and I got cosines. You get whatever you get for a particular problem. And now, what's convolution? I take matrix J, I take its Fourier transform. I take matrix H, I take its Fourier transform. And Fourier transform diagonalizes both because every operator that's allowed must be translation invariant. So this is good base for everybody. So they only have elements on the diagonal after they have been Fourier transformed, both of them. But we know how to multiply diagonal matrices, right? The diagonal elements will be G0, H0, and so on down the diagonal. Tuck, tuck, tuck. And there'll be 0 every place else. In other words, product of these two matrices. On the left-hand side, it looks like, I had a matrix, I transformed it, I got a matrix, I multiply them. But if I've transferred them in their intrinsically correct basis, which is the only basis when you have translation invariance, then I get that they're actually just, products of diagonal elements, just two numbers, K, K, tilde, H, K, K. No sum, I'm looking at a kth element. Times delta JK, only on diagonal. So that's now the amazing power of symmetry. It's made the problem so simpler, so faster. Now I stop Fourier transforms. Now there are amazing things to learn. In practice in this millennium, you have to understand how fast Fourier transform works, which is this plus a little more algebra. And in the 19th century, you have to understand that these things can approximate piecewise functions used in engineering, like sawtooth or on-off switches and stuff like that. But at cost, that's called Gibbs phenomenon, as described well in all the books I've given you, so I won't do it.